So just like for the idea of the line integral, I'll take a copy of this picture up here just so we can kind of recall what it is we're doing here. So suppose that our surface S is immersed, right? Say is surrounded. Say immersed is probably a better word. In a scalar field or better yet, that the scalar field is defined, this scalar field we call phi of r, on the surface. So this could be like a temperature field, or it could be a the mass density field, right? If it's the, so for example, like phi of r could be the mass density or the charge density. And if it's a mass density, it's measured in kilograms per meter squared, because it's the surface mass density. Or it could be a charge density, in which case it'd be measured in coulombs, which is the unit of charge, per meter squared. Alright, these are just a couple different examples of what phi could be. But assume that we have this scalar field defined on the surface, and we want to figure out the total accumulation of this scalar field on the surface in question. Well, not much changes in our Riemann sum approximation, except for the fact that now at multiple different points on the surface, and multiple different points in each one of our subpartitions, right, we have to evaluate the value of the scalar field on each one of the points on this partition. So we have to evaluate the scalar field, we'll call it phi on r of ui star vj star, where ui star vj star is some sample point inside each one of these subintervals. So we choose one sample point. It could be the left corner point, the right corner point, the midpoint, but the idea is that we're assuming that these partitions are small enough that this function phi, or phi at r of ui j star, is approximately equal to the value of phi, the value of the scalar function phi, inside the rectangle. So I will say inside or on the rectangle, which is on this patch of surface right here. so on the surface patch. And then the idea then is that the approximate accumulation of this function phi on the surface patch is then going to be on the entire surface as a whole is going to be the summation, the double summation like before, from 1 to n, 1 to n, of this value of the scalar function on the surface patch multiplied by delta Sij. And this is because if delta Sij is an approximation to the area, and this is the approximate constant value on each individual patch of phi, and phi is, say, if phi is a mass density function, then this mass density function multiplied by this area gives us a total approximation to the amount of mass on that piece of surface. And so the exact value is the limit as n goes to infinity of this approximate double sum, which is exactly the double integral over the region D of the scalar function RUV. Remember, delta Sij is approximated by the magnitude of Ru cross Rv du dv. And this is what we call the surface integral of the scalar function phi. So the surface integral of a function phi is exactly equal to this double integral right here. And this really kind of sheds some light on what we mean by the surface integral of a function, and you can clearly see that the surface area is the surface integral of the scalar function 1, the constant function 1. So let's see an example of this. Suppose we have a spherical shell. And we want to find the charge on the shell if the minimum value of the charge density is 1 is kilogram per meter squared, or kilogram per square meter, and it is proportional to the square of the height, the z coordinate. And this gives us relatively straightforward z dependence on the density function. So the charge density function as a function of r position is just going to be equal to 1 plus z squared. And we can even see a direct picture of this. If we go through and make a plot of this. Specifically, if we go through and plot what this is going to look like, it exactly looks like this, where the minimum charge density here is 1. That's this dark red. And as we go up, the charge density gets larger and larger and larger until it hits its maximum value right here at the highest point on the sphere. And same thing with the lowest point in the sphere, because it depends on z squared. So this problem, we're looking for the total charge on this sphere. The total charge is going to be the surface integral over the surface S of this density function phi, or the surface integral of the function 1 plus z squared. Which is going to be the double integral from 0 to pi, 0 to 2 pi, 1 plus in z squared here. So we'll call it the sphere of radius r. I don't think I mentioned the radius. This is a spherical shell of radius r. Be 1 plus z coordinate squared, which is r squared cosine squared of v, and ds, remember, is r squared sine of v, du dv. Which breaks up into two separate double integrals. This will be r squared times r squared is r to the fourth times cosine squared of v times sine of v du dv. And this first surface integral we've already, or this first double integral we've already evaluated. This is just 2 pi times r squared, or not 2 pi, 4 pi times r squared, or the surface area of the sphere. And we have to add to this whatever this surface integral right here becomes, or this double integral right here. So sure enough, when we go through and do this, this is a relatively straightforward integral to evaluate. It just becomes r to the fourth And the function here only depends on v, so the first integral with respect to u is just going to be 2 pi times the integral from 0 to pi of cosine squared of v sine of v dv and we can do a substitution here. We'll call it w substitution of w is equal to cosine of v, which means that dw is equal to negative sine of v dv, and the total charge on the sphere is 4 pi r squared plus 2 pi r to the 4th, and it's the integral, when cosine, well, v is u, cosine is cosine of 0, which is 1. When v is pi, cosine of pi is negative 1. And then we have w squared, and sine of v dv is negative dw. The total charge on the sphere is 4 pi r squared plus 2 pi r to the 4th times the integral from negative 1 to 1 of w squared dw, which is 4 pi r squared plus 2 pi r to the 4th times w cubed over 3, and we have to evaluate this at 1 and negative 1. And when we do that, we get 1 over 3 minus negative 1 over 3, which is going to be positive 2/3. So the total charge Q is going to be 4 pi r squared plus 4 pi r to the 4th over 3, or 4 pi r squared multiplied by 1 plus r squared over 3. And this is coulombs. So this is the total charge, electric charge on the sphere. And this is really, really nice. It's showing that we can directly go through and use this idea of the surface integral. So suppose that we have a special type of surface. We can simplify the equation for the line integral over that surface a little bit. And I shouldn't even say just a little bit. It actually simplifies it considerably. So in a multivariable calculus course, you typically deal with the graph of functions. So if you have say a function of two variables, and we'll title this Simplification of Surface Integral for Functions of Two Variables. And specifically we'll say simplification of this surface integral for surfaces S that are functions of two variables. The sphere and any surface that sort of maps over on itself can't be expressible as one single function of two variables. But this is why one of the main reasons that we kind of go to parameterization for more general surfaces. However, many surfaces can be expressible as a graph of a function of two variables. Specifically, right, the graph of a function of two variables is any surface such that z is equal to a function of x and y. And for such a surface, we actually have a simplified form for the surface integral. The formula simplifies by a lot, very, very nicely. Specifically, if we think about parameterizing the surface, right? So if this function is defined on for x, y in some domain D in 2D space. D is a subset of two-dimensional space. So the parameterization that we can take for our surface in this case is going to be R of uv, where we'll just identify x as u and y as v. And so our parameterization for a surface that's expressible as, the graph of some 2D function is going to be the following vector function. Well, x is u, y is v, and z is whatever the value of that function is. So f of uv. And this is the correct way of parameterizing the graph of any function. Right? This is, by the way, possible for parametric curves as well. If you have a curve that's expressible as a function of your variables, a simple parametric curve, which we saw in the gravitation example when we covered the gravitation example in the previous lecture. Now, first things first, we need to calculate the normal vector for the surface integral here. So we're going to need the partial derivative of r with respect to u, which is going to be 1, 0 in the partial derivative of f with respect to u. And then the partial derivative r with respect to v. Partial derivative of u with respect to v is 0. The partial derivative of v with respect to v is 1. And the partial derivative of f with respect to v is going to be whatever the partial derivative of f is with respect to v. Right. Remember, this is because for our surface, z is equal to the graph of f of xy, which in this case is f of uv, if we identify x with u and y with v. So that means the normal vector to our surface is going to be the cross product of ru with rv. Or I shouldn't say the normal vector because it's not a unit vector in general. So we'll just go through and calculate this cross product, which will be perpendicular to the surface, not necessarily a unit length. And because it's the cross product of this vector right here and this vector right here, the magnitude of this cross product, or the actual value of the cross product vector, is going to be 0 times this minus df du times 1. It's going to be negative df du the y component is going to be negative this times this minus this times this. So it's going to be negative df dv for partial f partial v. And then the z component is going to be 1 times 1 minus 0 times 0, which is just 0. Or just 1. 1 minus 0, which is 1. So there you have it. This is our RU cross RV. And we know that in the formula for our surface integral of a scalar function, we don't necessarily need this normal vector, but what we do need, or we don't need the normal vector in this direction. We will when we get to the integral of a vector field. But for now, all we need is the magnitude of this vector. So the magnitude of RU cross RV is going to be equal to the square root of 1 squared plus df du squared plus df dv squared. And what that means is that the surface integral over a surface S of the function phi is going to be equal to the double integral over the region D of the scalar function phi at our surface, phi of RV, or R of UV, times the magnitude of RU cross RV du dv, which is exactly equal to the double integral over D of the scalar function of RUV times the square root of 1 plus df partial f partial u squared plus partial f partial v squared du dv. Right, which is a little bit simpler to use and to go through and calculate. This also means that if you want that to calculate that normal vector for such a surface, you can go through and do that, and that the unit normal vector to the surface for such a surface is going to be this vector divided by the magnitude of this vector. So the unit normal vector for this surface, such a surface of a graph of a function of two variables, is going to be this vector divided by its magnitude, or the vector 1 over the square root, this square root, 1 plus the derivative of f with respect to u squared plus the derivative of f with respect to v squared. So it's 1 over this times this vector right here. This will be the unit normal field for every point on this graph, which will be important a little bit later on. But the point here is that this is a very, very useful formula for problems that can be written in surfaces that can be written like this, and it does greatly simplify the process of going through and calculating. So for instance, let's consider the following example. We'll consider finding the surface integral of the function phi of r equal to 2y squared plus z over 4x squared plus 4y squared plus 1 to the 1/2, the accumulation of this function over the portion of the surface of the paraboloid x squared plus y squared plus z is equal to 4, for which z is greater than or equal to 0. Now, the best way of starting any problem like this is to try to get some idea of what the surface you're dealing with looks like. Right, and we can do this directly using the idea of cross sections. This is always how you can kind of visualize what a surface is going to look like if you figure out what it looks like in terms of some of its cross sections. So, given that we're looking at the surface, z is equal to 4 minus x squared minus y squared, which when x is equal to 0 gives us the curve z is equal to 4 minus y squared, which is a parabola that's opening downwards and goes up 1, 2, 3, 4. So it goes up 4 in the z-axis. At y equals 0, it's equal to 0. And then at y equals 2, z is equal to 0. So it looks sort of like this. Let's just try to get a nice curve right here. Perfect, right there. So kind of like this. And likewise, when y equals 0, we get the equation z is equal to 4 minus x squared, which again, we go over 2 in the x direction. When x is equal to 0, it's up here at z equals 4, and it stretches down to this point right here at x is equal to 2. And lastly, if you consider this function at z equals 0, you get the equation 0 is equal to 4 minus x squared minus y squared, or x squared plus y squared is equal to 4, which is a circle of radius 2 along the y-axis. Alright, so this is our surface right here, our surface S. You can clearly see why it's a paraboloid. It's a paraboloid that's opening downwards as you get larger and larger and larger in x and y. And not only that, but this paraboloid is immersed in this scalar function right here. So it's immersed in a scalar field that's governed by this scalar function. You can think of this scalar function as being like some sort of density function, right? So a charge density or a mass density. Right, but the idea here is that this is exactly what we're thinking of this function as on this surface S. So we don't always have to make a nice visualization of this, but it is nice to get a small sort of like diagram representing the surface. And if possible, it's also nice to get a visualization of this. So if we go through and open up our Python window, the Python code, I went through and I coded up that code that plots a scalar function on a given surface. And if we run the code for this example, sure enough, this right here is a nice picture of exactly what we're talking about, where this is the x-axis, the y-axis, and the z-axis. You have this paraboloid that's opening downwards. And this right here is a plot of the function itself, the scalar function on that surface. You see that its highest values are up here at around 4, and its lowest value is around 0, down around here. And as you move over the surface, right, the value of this function changes. So we're going to go through and actually compute exactly what this value is going to be of the surface integral of this function. And by the way, you'll notice that this is exactly in the form to apply that simplified formula that we derived, because this is just a function of x and y. Here, z is a function of x and y for this surface. So that formula in terms of x and y for the surface integral is equal to the double integral over this region, this domain D, of the function phi of r of xy times the square root of 1 plus df dx squared plus df dy squared dy dx. So in order to use that formula, and you notice that that formula, to formally get that formula, I reparameterized the surface in terms of u and v. But for this problem, because we have f as a function of x and y, we can just take x and y as our two parameters, u and v, on the curve, and it exactly matches this formula right here, which is really nice. If you want to, you can always parameterize in terms of u and v, but it's not necessary as long as you're properly using the formula. So in order to evaluate this, we first need the partial derivatives of f with respect to x and f with respect to y, which we have. Right? The partial derivative of f with respect to x is going to be the partial derivative of 4 minus x squared minus y squared, which is equal to negative 2x. And a similar calculation will yield that the partial derivative for f with respect to y is equal to negative 2y. Also, phi of r of xy is going to be the function phi with x and y and z plugged into the function phi. So function phi of r of xy is going to be 2y squared plus z, which is 4 minus x squared minus y squared, divided by 4x squared plus 4y squared to the plus 1 to the power 1/2. So when going through and evaluating our surface integral, this ends up simplifying to the double integral over the domain D of 2y squared plus 4 minus x squared, and simplify that a little bit. 2y squared minus y squared gives us y squared. So this is going to be 4 plus y squared minus x squared. divided by the square root of 1 plus 4x squared plus 4y squared. This is what phi of r of xy is. And then we multiply this by the square root of 1 plus df dx squared, which is going to be 4x squared, plus df dy squared, which is 4y squared. dy dx. And so we get a really nice cancellation here. And our surface integral over S becomes equal to the double integral over d of the function 4 plus y squared minus x squared. And this is just a nice double integral that we can go through and evaluate. But we do have to be careful because this domain D is a non-rectangular domain. Specifically, right, it's this upper quadrant of the circle of radius 2 in the xy plane. So we need to figure out what the correct bounds are for this region. Because D is a set of all points x, y in two-dimensional space such that x squared plus y squared is less than or equal to 4. A circle of radius 2. So because of the polar symmetry in this region, the most natural coordinate system to do this double integral in is definitely polar coordinates. So if you remember, you should hopefully remember from your calculus, multivariable calculus class for double integration, polar coordinates gives you a dA or dy dx of r dr d theta. And this region is very, very nicely described in polar coordinates, or it's much nicer in polar coordinates. It's r theta for theta between 0 and 90, or pi over 2, and r between 0 and 2. So it's much nicer to describe in terms of polar coordinates. So we're going to use that polar coordinates in our integration. That being said, you can go through and do this integral in Cartesian coordinates. And I will include that at the end of these lecture notes so that you can see how to go through and do that in Cartesian coordinates. It takes a little bit of a long time, so I'm not going to go through and do it. But I always think it's a good exercise to go through and, if you can, do an integral in as many different coordinate systems as possible, so you really get a feel for how to do your double and triple integration. This is what I always encourage people to do in a multivariable calc class. So try to replicate my results by doing the integral in Cartesian coordinates as well in your notes. But I'll include that at the end of these notes so you can take a look through for yourself. So this double integral, when we write it in polar coordinates, is going to be 4 plus y squared. In Cartesian, in polar coordinates, x is equal to r cosine theta and y is equal to r sine theta. So it's going to be 4 plus r squared sine squared theta minus r squared cosine squared theta. And then dy dx is going to become r dr d theta. And our bounds are from 0 to pi over 2, and for r from 0 to 2. And trust me, this function looks a little bit more complicated than this function right here, but it is 100% worth it to do it in polar coordinates rather than Cartesian coordinates. Yeah, trust me on that, because I went through and did it myself in both coordinate systems, and it's definitely a little bit longer because of the non-rectangular domain in Cartesian coordinates. So we go through, and this becomes, by linearity, for r dr d theta, as this integral, plus the double integral from 0 to pi over 2, 0 to 2 of r squared sine squared theta minus cosine squared theta dr d theta. And it's actually not r squared, it'll be r cubed, because we have r squared here and r here. It'll be r cubed. And we can go through, and you see that this is going to be equal to the integral, the first integral here is with respect to r, so we can factor out the constant, and we don't have any functions of theta in here, so this really is just going to be the integral of 1 d theta for 0 to pi over 2 times the integral from 0 to 2 of r dr. This is going to be plus then the integral from 0 to pi over 2 of, and because this also does not depend on theta, it's going to be r cubed dr times the integral from 0, oops, this is from 0 to 2, this is from 0 to pi over 2. So nice thing about double integrals is that you can always split them like this if the two functions are multiplicative. And so this integral becomes 4 times pi over 2 times r squared over 2 from 2 to 0 plus r to the 4th over 2 from 2 to 0 times the integral from 0 to pi over 2. At this point, it's convenient to use the double angle formula for the sine squared minus cosine squared. So recall that sine squared theta minus cosine squared theta is the same thing as 1 minus 2 times cosine squared theta which is the same thing as cosine of 2 theta times negative 1. This is negative cosine of 2 theta and thus this will be equal to, well, 4 divided by 4 is 1. This is pi times 2 squared plus 2 to the 4th divided by 2 times, and this is actually negative, there's a negative sign here, and the integral of cosine 2 theta is 1/2 sine of 2 theta, and it's evaluated at pi over 2 and 0. So when we evaluate this at the endpoints, this is going to end up being 0 minus 0, so this entire thing is 0, and we're left with the answer of 4 pi.